Let's talk about roots. Um, the main thing to remember is what they mean, the symbols mean. Sometimes students are not completely aware of what the symbols mean. So let's make sure we do. We understand what is going on. Um, a square root of a. I'm putting an underline to state that this is the number a, not the article a as in the English article. It's just the number a. So a square root of a is a number b, so that when we square b, we get back the a. So again, that's a square root. Something to note is that positive numbers have two square roots. So 9, the number 9 has two square roots, 3 and negative 3. But wait a minute, there's more to this. The principal square root, so mind here we're defining what a square root is versus the one, a single, principal square root. Big difference. So a square root, the principal square root of a positive number a is the positive of the two square roots of a. See, again, 9 has two square roots, 3 and negative 3. The principal one is the positive of the two. And the symbol we use is this one. So this symbol means the principal square root. So from now on, this means 3, not plus minus 3, not plus minus 3. It is, so this symbol itself is what we are defining as the principal square root. Now, having said that, we do get lazy and say this is the root of 9. But technically speaking, we should say this is the principal square root of 9, and this is the symbol for the principal square root of 9. So please be aware of that. That is very, very important. There are two roots, yes, but when we write this symbol, we mean the principal square root of 9. Yes. And one other thing, do not confuse solving the equation, this equation, versus writing down that. That's not the same thing. The solution to this is, yes, plus minus 3. This is just 3, not negative 3, because we're not solving the equation. See, here we're asking for all the possible numbers so that when we square them, we get 9. Here, we're not asking for all the possible numbers so that when we square, we get 9. This symbol calls for the principal, which means in this case, the positive square root. Positive square root of 9, which is only 3, exclusively 3. So please be very, very aware of that. That's an important differentiation. And that's one of the things we may be testing when we are testing for this concept. Okay. We're going to simplify some roots. Yep. Simplifying roots. Okay. So if we have just the square root of a, that does not simplify, leave it alone. If we have a squared and we want to simplify that, well, on one hand, we are squaring, and then on the other hand, we are choosing the positive root. So no matter what the initial number was, we're going to end up with a positive answer. But the initial number could be negative to start with. We do not know that. So the answer to this is the absolute value of a, not a, but the absolute value of a. Now, if we know in advance, or if we have additional information that tells us that a is positive, then of course, by all means, that's going to be equal to a. But as is, no. We cannot do that. We cannot assume that this is positive. We have to have the absolute value. Now, if we want to simplify a cubed, we are going to have the same thing as the absolute value of a. Well, a has to be positive in order for this to make sense, because if it was negative, we wouldn't be able to do that. So let me erase this real quick. It's just a, yep, square root of a, if it makes sense. What I mean by that is, see, there's one thing within this is a fact. Okay. Within real numbers, we may not be able to find a square root of a negative number. Yeah. So in fact, we were doing that back here. In this case, we have to assume a is non-negative. In this case, we are assuming that a is not negative. Otherwise, this wouldn't make sense. Square root of a to the 4 is a squared. And you may be thinking, wait a minute, shouldn't that be the absolute value of a squared? No, because whatever the number a is, when we square it, we're going to end up with a positive number. So in this case, it doesn't matter whether the number is positive or negative. Here, on those two cases, we have to add that condition on a. So things get a little tricky, because it isn't true that we can just do about anything. We have to have special conditions for some things to happen or to work. A to the 5, the square root of a to the 5 will be a squared root a, again, assuming that a is positive. Well, actually, non-negative, because a could be 0. The 6, I mean, the square root of a to the 6, is a cubed. See, but we got to be careful. A cubed. But if a was negative, when we cube it, we will end up with 3 negatives, causing this to be negative. But this should be the positive, the principal square root. So because this could be negative, we have to anticipate that it could be negative. We have to put absolute value into this, because a square root, in this case, means the principal square root, which means the answer has to be positive if there's an answer at all. A to the 7 is equal to a cubed square root of a. And again, we're assuming that a is non-negative. A to the 8, the square root of that, is going to be a to the 4, no matter what the value of a is. Square root of a to the 9 is a to the 4 square root of a. And in this case, we are assuming that a is non-negative. Square root of a to the 10 is a to the 5, but it could happen that this answer is negative if a is negative to start with, because we would have 5 negatives multiplying each other. But this is the principal root, which means it has to be positive or 0. So to make sure that this is positive, we have to put an absolute value, etc. The same pattern continues. So we have square root. In this kind of cycles, let's see, 1, 2, 3, 4, square root again. 1, 2, 3, 4, square root again. So every 4 we end up with a square root. Here we got an absolute value, and every 4 we have an absolute value. 1, 2, 3, absolute value. 1, 2, 3, absolute value. Actually, here in the square root, it's every other one. Square root, square root, square root, square root, square root. Yep. Anyway, please review this table. It is an important table to review. Yep. Yep. And pay attention to the conditions. Close attention to the conditions. There's an alternative notation. The square root of a can also be written as a to the 1/2. The square root of a squared can be written as a to the 2/2. In this case, which is, by the way, a to the 1, which is a. But this contradicts what we are saying here. So we have to impose an extra condition that a is non-negative. So we have to add the extra condition. Otherwise, the condition is assumed. So in this case, it is assumed, it is understood that a is non-negative. Boy. So let's see this one. This one is a to the 3/2, which does not simplify. All right. Well, no, it does not simplify. And in here, we're assuming that a is positive. So let's see where this takes us. A to the 4 is equal to a to the 4/2, which is a squared. And this is going to be non-negative no matter what. Square root of a to the 5 is a to the 5/2. Yep, and we are assuming that a is positive. So in this case, we have to assume that, so we have an extra condition when we simplify fractional. Boy, this gets a little complicated. Let's see, with this guy. This is the same thing as a to the 6/2, which in turn is a to the 3. But in order to guarantee that this is positive, because this is the principal square root, we have to assume that a is non-negative. Yeah. Boy, this is just the square root. There's more to this when we talk about the cubic root. So let's define the cubic root now. So this is a definition. The cubic root of a, the number a, is the number b such that b cubed is equal to a. And the symbol we use is same as the square root, but we have a 3 in there, a. All right. Now, I want to make emphasis of the difference among the definitions. When we define the square root back here, a square root, we use the article a square root. Here, I did not use a, I said the, and that is intentional because there's only one cube root. That's it, just one cube root. There are 2 square roots of a positive number, but there's only one cube root regardless of whether the number is positive or negative. There's only one. So we gotta start paying attention to those little details. Again, we're using the article a versus the, implying that this is unique, that there is only one. And indeed, there is only one cubic root. So the cubic root of 8 is 2, not negative 2. Why not? 2 and only 2. That's it, nothing else. It cannot be anything else. The other candidate, I suppose, would be -2. But -2 cubed means -2 times -2 times -2 would give us -8. So that is another thing that happens with the cube root. We can find the cube root of -8. That would be -2. And only -2, nothing else. So let me write this again here. The square root of 4 is 2, and not -2, and not -2, because this symbol means the principal square root. The square root of -4 does not exist. Does not exist within the real numbers. So we cannot do that. But there's a second square root, which is not the principal of 4, which is -2. The cube root of 8, on the other hand, is 2, and only 2. The cube root of -8 is -2, and only -2. Yep. So let's draw a table similar to the table we did with the square root. And this is an interesting table, the table we're going to draw. Yes, so let me just have the same kind of, simplifying roots. Heading, simplifying roots. So the cube root of a has to stay as is. We cannot simplify it. The cube root of a squared also has to stay as is. That is an interesting thing that did not happen before. By the way, another notation for this is a to the 1/3, and this is a to the 2/3. And here there's no ambiguity. There's no a has to be positive or negative, as with the square root. Square root is a little tricky. The cube root of a cubed is just a. That's how it simplifies. Yeah, I guess initially we would have a to the 3/3, which is a. The cube root of a to the 4 is a times the cube root of a, which can also be written as a to the 4/3. By the way, when I ask to simplify, the mid column is the one that I would prefer, the one with the root. This looks a little funny. When you're writing, so let me rewrite this again. When you're writing a and then the cube root of a, make sure the 3 is inside of this little groove in here, because if you put it a little bit to the left, it may look like you're doing a cubed times the square root of a. So you gotta watch out. The cube root of a to the 5 is a cube root of a squared. That's how it simplifies. It can also be written as a to the 5/3. However, in many of the problems, I'm going to ask you to write the answer as in the middle column to simplify, keeping the root symbol. The cube root of a to the 6 simplifies nicely into a to this, a squared. A squared. And another way to write this is a, here I'm doing it again, a to the 6/2. Yep. So this is again the simplified form of this or that. Yep. Let's do a couple more. The cube root of a to the 7 is a squared times the cube root of a. See, we got to be careful so those two don't mix up. So this is the exponent of a outside of the root, and this is the index of the root. Yep. And this is, by the way, the same thing as a to the 7/3. Now, 7/3 is an improper fraction. If you turn it into a mixed number, we're going to end up with 2 and 1/3, and that's where the 2 and the 1/3, 2 and 1/3 comes from in this expression. The cube root of a to the 8 is equal to a squared cube root a squared, which by the way is a to the 8/3. But again, this is the one we want. The cube root of a to the 9 is a cubed, and that can also be written as a to the 9/3. But of course, we're not going to write this as our final answer because that fraction is not simplified. We have to simplify it. Okay. Practice, practice, practice your cube roots and your square roots. Finally, for this video, we want to learn we want to review how to rationalize denominators and how to rationalize numerators. So rationalizing denominators and I'm going to show you with examples. So let's say you have 7 over the square root of 3. So rationalizing the denominator means that we don't want a fractional exponent in the denominator. So this is a little misleading in the sense that we are rationalizing the exponents of the denominator. Actually, I think I misspoke. Anyway, rationalizing the denominator means getting rid of the root, there we go, in the denominator. So the practice is that we multiply by the square root of 3 over the square root of 3, and we end up with 7 square root of 3 over, and square root of 3 times square root of 3 is 3. And that's it. That is the right. So we don't have a root in the denominator anymore. We have to pay a price. Now the root is in the numerator, and there is another extra number to work with, the 3. But oftentimes, this expression is easier to work with than this one. Not all the time, but sometimes that expression is easier to work with. Let's do a few more examples. 1 over the square root of 2. So assume you start with that, multiply by the square root of 2 over the square root of 2 equals square root of 2 over 2. 3. Now this next one is going to have an extra step. So multiply by the square root of 2 over the square root of 2 as we did before. And we have 10 times the square root of 2 over 2. But now we can simplify the 10 and the 2 to end up with 5 times the square root of 2. So this one has an extra step. Watch out for that because you would leave some points on the table if you don't take this extra step. 6 over the square root of 3 times square root of 3 over the square root of 3, which is just 1. So we end up with 6 times square root of 3 over 3. And one more time, we got to simplify that to square root of 3. Oh, okay. So those 4 examples are the easy ones. Now let's make this not as easy. Example 5. 7 over the cube root of 5. Okay, that's not easy, or not as easy as the other one. We don't want to do a multiplication of the cube root of 5 over the cube root of 5, because we end up with the cube root of 25 in that case. Let me repeat that. If we did the cube root of 5 over the cube root of 5, we end up with the cube root of 25 in the denominator. And there's no cube root of 25, at least not an integer. We want to end up with an integer cubed root of something. or we want to end up with an integer in the denominator. So in order to simplify a cube root, we need 3 of the same factor. Right now we have a 5. So we need 2 more. So we multiply by the cube root of 25, which is 2 more 5s, over the cube root of 25. That's going to give us 7 times the cube root of 25 over the cube root of 125, because 5 times 25 is 125. All right, so that is 7 times the cube root of 25 over 5. Whoa, that is not an easy one. So pay attention to the index. 6. 1 over the cube root of 4. Okay, now this is tricky. This is not as easy as that one. 4, think of 4 as 2 2's. 2 times 2 is 4. We need 3 of the same factor to get rid of the cube root. So we really need to multiply by the cube root of 2 over the cube root of 2. I know you may be thinking, wait a minute, aren't we supposed to multiply by the cube root of 16? That's overdoing it. See, we got to pay attention of how many factors we have in a cube root. If we have 2 factors, 2 times 2, then you just need 1 more. If you have 1, then you need 2 more. So things are not as straightforward as we may think. And that's okay. That's the way we want it to. I mean, that's the whole point of math. If somebody thinks that math is just, hey, tell me what formula, I'll use it and I'm done. We gotta pay attention to the details of what is given. Yeah. Okay, so this is the rationalized answer. 7. Okay. 10 over the cube root of 2. Okay, this one is more like it. We got cube root of 4 over cube root of 4. Because we had a 2, so we need 2 more 2's. So that is 10 times the cube root of 4 over, and we know this is going to be the cube root of 8. You know, cube root of 4 times cube root of 2 is cube root of 8. And the cube root of 8 is 2. So we can save ourselves some time because we still have to simplify those 2. Here, there's nothing to simplify, neither is there here, but here we have to. So this is 5 times the cube root of 4 as our final answer. Oh, I missed to tell you something, and it's okay because we can redo this again. So 6 again. I wanted to show you what happens if we multiply by the cube root of 16, because you could apply that rule if you wanted to. Just whenever you have a cube root and a number, just square the number and use that on top and the bottom. Will it work? Yes, but not as smoothly as you may think. So cube root of 64. 4 times 16 is 64. The cube root of 64 is 4. But here's the thing. Cube root of 16 over 4, which does not look like this answer, the cube root of 2 over 2. And the reason is because this can be simplified. There is 4 2's in 16. 2 times 2 times 2 times 2 is 16. There's 4 of them. And every time you have 3 of those, you can simplify that. So this is the same thing. Let me write what I am saying. So this is the cube root of 8 times 2, that is 16 over 4, which is the cube root of 8 times the cube root of 2. And again, I did not explain at the beginning the properties of roots, such as splitting factors under a root as 2 roots. Any algebra book will have that, so please refer to that. And then the cube root of 8 is 2 times the cube root of 2 over 4. And now we simplify those two to finally end up with the cube root of 2 over 2, which is the same answer we had up here, cube root of 2 over 2, cube root of 2. But look at the number of steps we have to do. Okay, it looks like we were going to simplify the steps, you know, just do the square of that and multiply. Yeah, it does work initially, but then there's more to do. So that is very inefficient, and ultimately it is not a very good idea to do that. Example 8. Rationalize 6 over the cube root of 9. Again, it is tempting to multiply by the cube root of 81 over the cube root of 81. Don't. Analyze the 9. The 9 is 2 3s, 3 times 3. So we want to multiply by a single 3. Otherwise, we're going to end up with this mess that we had here. We don't want to do that. So we end up with 6 times cube root of 3 over cube root of 27. Of course, the cube root of 27 is 3. So 6 times cube root of 3 over 3. Simplify those, and we end up with 2 times the cube root of 3. Now, we can rationalize, or we may rationalize the numerator, but the denominator, but we may rationalize the numerator. There are instances when we want to get rid of the root in the numerator, even though it may show up in the denominator. So we have to be able to do that if needed. Okay, so let's talk about rationalizing the numerator. Okay, example 9. Square root of 7 over 3. Okay, this time I don't want the numerator to have a root, even if by doing so we end up with a root in the denominator. That's okay. That's what rationalizing the numerator means. All right, multiply by the square root of 7 over the square root of 7, and that's going to give us 7 over 3 times the square root of 7. That looks not very natural, because we typically want to rationalize the denominator. But there are instances when we want to do that, so we got to be proficient at that. 10, example 10. How about square root of 10 over 5? Multiply by the square root of 10 over square root of 10. As we've done earlier, we end up with 10 over 5 times square root of 10. But then the 10 and the 5 simplify, and we end up with 2 over square root of 10. Example 11. Square root of 15 over 3. We want to rationalize the numerator, multiply by square root of 15 over the square root of 15. So we end up with 15 over 3 times the square root of 15. But then the 15 and the 3 simplify, and we end up with 5 over square root of 15. Okay, how about cube roots? 12 cube root of 49 over 3. Now, rationalizing cube roots is more tricky. 49 is, and we gotta step back and think, okay, what kind of number is 49? 49 is 7 times 7, 2 7s. So instead of multiplying by cube root of whatever 49 squared is, which is a gigantic number, like in the thousands, we multiply by the cube root of 7 instead. Because this already has 2 7s, and another 7 makes 3 7s, cube root of 3 7s multiplied together is simply 7. And the denominator is 3 times the cube root of 7. There we have it. There's no more to do. Very, very simple. Because we were thinking ahead of time and thinking that this is already 2 7s, and all we need is 1 more 7 to make 3 7s. Watch out for those details. I think I have 2 more examples to go. 13 cube root of 10 over 5. Well, this time we have only one 10. We need 2 more 10s. Cube root of 100 is 2 10s. Cube root of 100. Well, that is kind of weird looking. So when we multiply those two together, we get 1,000. The cube root of 1,000 is 10. So we end up with 10 over 5 times the cube root of 100. That does not simplify. But the 10 and the 5 do simplify as 2 over the cube root of 100. So there is our simplified version of this. Well, I shouldn't say simplified, rationalized in such a way that the numerator does not have any root anymore. And 14, oh, this is a good example. Cube root of 225 over 3. Now, I happen to know that 225 is the square of 15. Yeah, 15 times 15 is 225. Please double check that yourself. So there's 2 15s in this 225. So we want to multiply by 1 more 15. Imagine if you were multiplying by 225, 225 again, 2 more times. That would get huge. So we got 15, 15 from the 225. Another 15, that makes 3 15s. Cube root of 15 is 15. In the denominator, we have 3 times the cube root of 15. And of course, we have to simplify the 15 and the 3. So we end up with 5 over the cube root of 15. Practice, practice, practice. That's the only way to get better at all of this. All right, I'm going to stop the video now.